Alright, so starting our notes on quantum numbers, this is just basically a way to put everything together. Everything that we've been doing up to this point with energy levels and the shape of the orbitals, the whole SPDF, the orientation of the orbitals, basically what blank are we in whenever you do the orbital notation, orientation, orbital notation, they both start with an O. And then also, saying, well, what direction is the electron spinning? So every electron in every single atom has 4 quantum numbers that basically describe how much energy that electron has. And we're not going to do anything with these numbers. You can kind of think of it as, you're a little 3-year-old and you're learning how to count. You didn't start doing the addition or subtraction or math or algebra or any of the stuff with the numbers until long after you had learned what the numbers are. So you can just consider this to be the counting level of quantum numbers. We're not going to do any of the math with them. We're not going to plug them into formulas and equations and, figure out other stuff that you would figure out with these things. We're just going to learn how to find them. So the first quantum number that we need to label is the main energy level. And you guys played Electron Configuration Battleship on Friday. And so if you were, say, wanting to call out, how about vanadium? We're going to do vanadium. So where on the periodic table is vanadium? Well, if you were playing Electron Configuration Battleship, you would say that vanadium is 3D3. And it's this first number right here that is equal to N. So you would say vanadium has an N value of 3. And that's just simply the energy level that you're on. What energy level are you? And it kind of makes sense to say that as N gets bigger, the electron has more energy because it's on higher energy level. And because I'm sure you remember, okay, here's your nucleus. When you drew your Bohr diagrams, every time you drew an energy level, the electron that was in that energy level was farther from the nucleus than one that was closer in. So that's just a little point to point out there too. And then also, if you remember that the number of orbitals in an energy level is equal to N squared. So like right here, in energy level 1, the maximum number of orbitals was that S orbital. Remember, S's only have 1 orbitals to them. And then 2, you had S and P, and S has 1, P has 3 orbitals. This is the number of blanks that you draw whenever you're doing orbital notation. 1 plus 3 is 4. Energy level 3, you have S, P, and D. S had 1 blank, P has 3, D has 5. Add them all up and you get 9. Energy level 4, your S, P, D, and F. 1 S orbital, 3 P orbitals, 5 D orbitals, and 7 F orbitals all add up to 16. And this is the number of orbitals. This is not number of electrons. If we wanted to do that, that would be your 2, 8, 18, and 32 that you were probably forced to memorize as an 8th grader. So moving on to the second quantum number, it's symbolized with an L, and I actually usually write it like that so that you can definitely tell the difference between a 1 and an L. And this is your shape. This is your S, P, D, or F. Number of possible shapes is equal to the energy level. Just a little help you remember. So like the 4th energy level has 4 possible shapes, 3rd energy level has 3 possible shapes, 2nd energy level has 2, and so on and so forth. The possible values for L range from 0 to N minus 1. So we were doing vanadium, which we said has an N value of 3. So that means the L value has to be somewhere between 0 and 2. Because N minus 1, N is 3, so 3 minus 1 is 2. So L has to range from 0 to 2. So we got to figure out exactly what it is. Well, we said that vanadium was 3D3. Well, D has a value of 2. So L is equal to 2. They just not arbitrarily. There's a very specific reason why they pick these numbers, but we don't have to worry about it. So they just pick these numbers. Anytime you're in an S, it has an L value of 0. Any P has an L value of 1. Look at that. The 1 and the L look exactly alike. So we have an L value of 2. And these are just some possible L values. If you want to write them down, you can, but it's not necessary. The third quantum number is M subscript L, or M sub L. And this tells you what direction is that orbital facing. Basically, it tells you what blank are you in. And I did not mean to put positive L to negative L. I actually meant to write negative L ranging up to positive L. So we already said with vanadium that N was equal to 3, L was equal to 2. So that means that M sub L can range from negative 2 all the way up to positive 2. Well, how do you know which number you have? Well, we did 3D3. So we actually draw the orbital notation of the D sublevels. So D's get 5 blanks. Label it as 3D. And then we fill in these 3 electrons, 1, 2, 3. And it's the blank that the last electron went in. Well, how do we label these blanks? Well, it starts at negative L. L was 2, so our first blank is negative 2. And then we count up by whole numbers. So negative 2, negative 1, 0, and then we start into the positive, plus 1, plus 2. So our electron, our last electron actually went into the blank that was labeled 0. So M sub L has a value of 0 in this particular case. And this is just a little reminder that each orbital can hold up to 2 electrons. So how do you tell the difference between this up electron here, or if instead of vanadium we did nickel, which was 3D8, and we would have 1, 2, 3, 4, 5, 6, 7, 8. How do you tell the difference between this electron and this electron? Well, that's where the 4th quantum number comes in. So the 4th quantum number just deals with, did you draw an up arrow or a down arrow? If you drew an up arrow like we did with vanadium, remember vanadium had 5 blanks, and it was 3 ups. So this arrow right here is an upward facing arrow. So N was 3, L, because we're in the D sublevel, was 2, M sub L, based on the label of our blank, was 0. So M sub S, since we have an up arrow, is this one, positive 1/2. Yes, you have to put your sign on this one. You can't assume that it's there. And so these are the 4 quantum numbers. That's a 2, by the way, in case you can't read that. And that's all there is to it. Energy level, sublevel, blank, which blank you put your last electron in, and is your arrow an up or a down. So this is just kind of what I've been doing this whole time, connecting it to the orbital notation configurations that we've already done. You draw out the orbital notation for the last sublevel filled in an atom, basically what would you call out for electron configuration battleship, and then draw that orbital notation. Circle the last electron inserted in that sublevel and find the 4 quantum numbers for that electron. You can either circle it or you can highlight it like I was doing on the last one. So here's our examples. 4 quantum numbers for the electron of highest energy in nitrogen. That means the last electron put in. So if you were playing electron configuration battleship, you would call out 2p3. And again, y'all pause these if you need to, if you want to figure it out on your own before I start going through the answers. So P has 3 blanks, and we're filling in 3 arrows. And our last arrow is this guy right here. So N is equal to the energy level. L is equal to the sublevel, and P was just given, go back and show you this one. P was given a value of 1. Notice all these P's are 1s. So we can come back here. So 2p3, 1, 2, 3, 1, 2, 3. N is 2, L is 1. M sub L, we need to label our blanks. 0 always goes in the middle, and then you can just count down and count up. And so our last electron went into the positive 1 blank, and then M sub S, since it's an up arrow, is positive 1/2. Example 2, for sulfur, again, pause it, work it out, and then hit play. Sulfur is 3p4. So I'm going to draw that P sublevel again, this time with 4 electrons in it. And our last one was this guy right here. Make him stand out. So N is equal to the energy level, which is 3. L is equal to the value assigned to the sublevel. The value for P is 1. M sub L is our blank labeling, so 0 goes in the center, count down to the left, count up to the right. So our last electron went into the negative 1 blank. And m sub s, since we drew a down arrow, is going to be negative 1/2. Last example, oh, I still labeled it example 2, my bad. Example for iron. Iron is 3d6. So I'm going to draw out 1, 2, 3, 4, 5, put 6 electrons in there. Energy level is 3. D has been given a value of 2. M sub L, label the center one 0, count down, count up. Okay, our last electron was this guy. So M sub L is negative 2. And M sub S, since it's a down arrow, is negative 1/2. Alright, I did put one more in there. Calcium. Calcium is 4s2, so one lonely little blank. Both electrons go in there. This electron was the last one that we put in. So energy level is equal to 4. Sublevel, the value given to S, is 0. M sub L, since there's only one blank, the blank is labeled 0. And then M sub S, it was a down arrow, so negative 1/2. Okay, if you have any more questions, feel free to come on in for tutoring, and I'll help you as much as I can. See y'all tomorrow.